Hello and welcome to the second part of finite element mesh generation in STAAD. My name is Surajit Ghosh, and in this video I will discuss about the basic mesh generation options available in STAAD, how to generate a plate mesh with a hole, and few modeling challenge with basic plate mesh. I'm sure you have already gone through part 1 where I have discussed about infill plate generation and why we should avoid modeling using an unmeshed plate element. If a plate is not connected with other plates and members through corner node, then there will be multiple problems like overlapping plates or beam plate connectivity issue, and these modeling problems will produce erroneous results. Another major issue of unmeshed plate is incorrect force transfer and structural behavior due to improper connectivity between different elements. As an example, I have used this tabletop structure with a single unmeshed plate to replicate the beam slab interaction. This plate does not have intermediate connections with the beam, hence no force is transferred to the beam from the slab. There is no support at the plate edge and it just settles due to the applied load, resulting zero moment and shear in the beam. Once the plate is meshed, then it is properly connected with the beam and force is transferred to the beam, which produce correct analysis results like proper out of plane deformation or correct BMD of the beam. Just compare the two figures and you can easily understand the difference in structural behavior. For more details, you should go through part 1. So, we need to create a proper plate mesh to model a floor slab, shear wall, or any other surface. Now the question is, what should be the optimum mesh density or how to decide the mesh size required in a model? To answer this, we need to understand the basics of finite element analysis and how the finer mesh affects the analysis results. That part I will cover in another video. For now, just a hint, finer mesh increase the result accuracy as there are more number of internal points, but it will also increase the modeling time, rendering time, and analysis time. It is very hard to work with a large model with very fine mesh. So the mesh density must be selected carefully without hampering the overall efficiency of the model, and as this is an irreversible action, it should be fixed before modeling. There are two options available in STAAD for basic mesh generation: create mesh and plate mesh. Though the names are almost same, but the functionality of these two options are different. Create mesh option generates a new plate mesh within a specified boundary. Means if you want to generate a plate mesh from scratch by defining the boundary, then you can use this option. Whereas the plate mesh option is used to divide a large plate element into small segments. So it works only if a plate element is selected. If there is no plate element present or selected in the model, then this option remains inactive. I will use the same model that I have used in my previous video. Check part 1 to know more about this model. I have already created few unmeshed plates using infill plate option. To generate a plate mesh, either we can delete these plates and create new plate mesh from scratch, or we can divide the existing plates in small segments. I want to mesh this plate element first, and without removing the existing plate, we can mesh it using the plate mesh option. That's why it is also known as super element method. We can access the same mesh generation option from right click, generate plate mesh option, and from plate toolbar, plate mesh option. All these options are same, and the main purpose of this option is to generate a plate mesh at the location of the existing plate. In the back window, you can also see the message which indicates that we are going to mesh an existing plate. We can either generate a mesh as a polygonal meshing or like a quad plate meshing. There are several differences between these options. One of the major differences is polygonal meshing generates a triangular plate mesh with or without hole, whereas using a quad mesh option, we can generate either triangular or rectangular plate mesh without any hole. First, I am going to select quad mesh option. In the mesh generator window, detailed information of this rectangular plate like the coordinate values and length of each side is mentioned. This ABCD refers to the order of nodes used to generate the plate. Length information is very important for mesh generation. In FEA, it is always suggested to create a plate with aspect ratio close to 1. Maximum 4:1 aspect ratio is allowed, which provides satisfactory results. If you want to maintain an aspect ratio close to 1 or want to create a square plate mesh rather than a rectangular one, then you need to specify the edge division based on the length. This plate has 4 meter length at two sides and 5 meter at two other sides. So we can specify same edge division in all sides. Aspect ratio is very close to 1. This division number indicates how many segments will be created in that plate edge. 10 means that side of the plate will be divided in 10 segments with 0.4 meter length. Note that we need to divide this boundary in such a way that there is a plate node at this junction. It is required for proper plate connectivity. This plate edge is 5 meter long with a junction at 3 meter distance. Edge division 10 or 0.5 meter plate segments will add a plate at this junction. So it is okay. But if the junction is say at 3.3 meter distance, then either we have to create more plate segments or manually adjust the plate connectivity as discussed in part 1. There is another input, bias. We can skip this input or set this to 1 if we want to divide the boundary in equal parts. For unequal edge division, we need to specify proper bias value. It is the ratio of the largest segmented length to the smallest length. Program divides the boundary in such a way that first segment has the smallest length and last segment has the largest length, and ratio of these two equals to the bias. Just for an example how this works, I have specified bias as 4 at BC side of this 2 by 2 plate. For bias 1 with 10 divisions, plate edge is divided in 10 equal parts with 0.2 meter length. But for bias 4, 10 unequal segments are created. First segment length is 0.091 meter and last segment length is 0.363 meter, which is exactly 4 times the length of the first segment. Length of the intermediate segments are calculated by interpolation. You can reverse this order by specifying negative bias value. For this meshing, I want equal edge division with bias 1. Finally, we can generate either a triangular plate mesh or a rectangular mesh. With these inputs, a rectangular equal division plate mesh is generated in the same place of the existing plate. This is the easiest way to mesh an existing plate. Also, you can notice these meshed plates have proper connection at this junction with the secondary member as well as with other plates. Let's consider the next panel. For this panel, I want to generate a quad plate mesh, but it is a bit tricky. This edge is already divided in 6 parts, and if we divide this plate edge in 10 division, then there will be plate-to-plate connectivity problem as discussed in first part. So for this plate, I am going to divide all the edge in 6 parts. Now these segmented plates are properly connected at this edge, but not at this edge. We need to mesh all the panels and adjust the boundary division in such a way that all plates are properly connected. We can also select multiple plates for meshing. Specify the edge division. For multiple plates, the edge division will remain constant for all plates at a particular side. And then select the meshing type to generate a plate mesh for all the selected plates. This is much more faster, but remember to adjust the edge division so that there is no connectivity issues. Now, this is a two-step approach. First, generate the plate and then mesh it. This method is used only if we need to mesh an existing plate. An easier solution is the create mesh option, which does not require an existing plate. We can select this option, and using the new mesh cursor, we need to create a closed boundary by selecting the corner nodes of a panel one by one in clockwise or anti-clockwise direction, and in sequence, not in a haphazard way, else the generated plates will be incorrect. After selecting all the nodes, we can either select the first node to close the boundary or press the right click. Same mesh generation options will appear, and this time I am going to select polygonal mesh generation as I am going to create a hole in this panel. If we select more than 4 boundary nodes, then automatically the polygonal mesh option will be selected. Quad option is available only if 3 or 4 corner nodes are selected. This mesh generation window is similar to the previous one. You have the node coordinate values, boundary division, and bias. Only the edge length is missing here. Note that the first node and last node is identical as it is required to form a closed boundary. We can also add a new node which will be used for meshing, but it must be entered in such a way that the boundary is closed. We can also delete any node. And from this small window, we can get an idea how the closed boundary looks like. The most useful option here is the inclusion of a hole. Using this, we can add one or multiple new holes within this mesh boundary, and mesh will be generated considering those holes. There are 3 types of hole which we can add: polygon, circle, and ellipse. In this panel, I want to add a triangular hole and a circular hole. Now, to generate a polygonal hole, we need to add new vertices and specify the node coordinate values of the closed boundary. There is no grid or manual selection option available, but we can copy the coordinate values from Excel and paste it in this table. You can notice this triangular region is now included in the panel. Also, we can add a new hole, set it as a circular hole, and provide the center coordinate along with the radius and edge division. This small figure is very useful. From here, we can easily identify whether these new regions are properly created within the boundary or not. We can also rename the hole, but I never use this. And once all information are provided, we can simply generate the mesh. For polygonal meshing, only triangular plates are created. No option is available to generate a rectangular plate mesh. See, a plate mesh is now generated with 2 holes. and you can notice the meshing is accurate near the holes. This plate mesh looks fine, and within this boundary, there is no issue with plate connectivity. But you need to mesh other panels cautiously so that the edge division match between different panels. This method of mesh generation is widely used to generate a plate mesh for slab or mat foundation or any FEM model like silo or retaining wall. Now coming to the problems. Though this method of mesh generation seems correct and easy, still there are few limitations for which it becomes very hard to use this approach for a medium to large scale model. First problem is we can't use this method to mesh the entire slab in one attempt. If we select the boundary points of multiple panels one by one and then mesh all the panels using polygonal mesh option, during mesh generation, program does not consider any internal beam or node. You can notice intermediate beams are not segmented or connected with the meshed plates, as these plates are not meshed in line with the beam. This will generate beam plate connectivity issue, and this mesh is not correct. So we need to mesh each panel separately and need to adjust the edge division manually, which is time consuming and kind of boring. Same problem occurs if there is any internal node. Consider a flat slab or mat foundation where the column is connected to the slab without any beam. During meshing, this slab column junction node will not be considered, which results in improper connection. Also, this approach is unable to identify the existing boundary nodes, like nodes which are generated from an adjacent mesh or nodes of shear wall mesh. That's why we have to manually adjust all the edge divisions. Also, it is not possible to create a separate mesh region within the mesh boundary which can be used further for load application or to assign different thickness, like to model the column drop cap portion or punching shear zone for mat foundation. If you want to divide the mesh in a line to apply a line load on slab, that is also not possible using this meshing approach. Lack of intelligence to identify existing beam or node during mesh generation. No option to generate meshing along a line or a region. These are some major limitations of the basic mesh generator. Also, I don't like the way the input of holes are specified in this module. It is very tough to find out the coordinates, and it would have been better if the hole can be specified using a grid. Final problem: if we generate a shear wall using this method, then plate mesh can be used only for analysis. The meshed wall will not be identified by advanced concrete design module for shear wall design. How to create a wall or flat slab model properly using FEM, which can be further used for design, that I will cover in my next video using parametric model option. Stay tuned and keep watching.